Welcome to this lecture about kinematic diagrams, discovering the amount of mobility that you have in a mechanism, specifically linkages. Now, it's called mobility or degree of freedom. It has to do with whether or not these mechanisms move or they don't move, whether or not we have one operator or more than one operator. We want to discover how our mechanisms move. Now, you've just finished sketching using kinematic diagrams of the mechanisms from the assignment in the book. Now, the next thing to do is to find out mathematically how we can discover how many operators or how these things move. Now, basically, we start out with knowing exactly what number will fit the amount of operators that you're going to need. If through this mathematical equation you come up with a 0, then this is called a fixed mechanism. That means that it's locked, it will not move. So when these mechanisms get fairly complicated, it's tough to discover what the mobility is. And so therefore, if you finish this formula and you get a 0, that means it's fixed, it's locked up. Number 1, if you get a 1 at the end of the computation, this is called constrained. Constrained means that you only need one operator in order for this mechanism to move. Now, the input could be by a human hand or foot or whatever it is, the human can move it, or it could be a machine, like a motor of some kind, that will activate it and will allow this thing to move. But you only need one operator. And third, we have what's called unconstrained, and that's equal to 2 or more. So that means basically you're going to have more than 2 or more inputs in order for this machine to operate. So 0, 1, or 2 or more will tell you how many operators and what the degree of freedom or mobility is for this particular mechanism. Now, this is the formula here. It was in the book, and I wanted to find the pieces for you. F is the degree of freedom. I'm using the abbreviation DOF, degree of freedom. N in the formula is how many links, and we know what the links are. They're either simple links or complex links. J, the joints, what kind of primary joints that you have. These primary joints are either these are pins or sliders. These are primary joints. So we count those. And then there's higher level joints. And these higher level joints have to do with some more advanced pieces in the mechanism. And this would be cams and gears specifically. So those are higher level joints. So now when you look at the formula then, you have those 3 unknowns in the formula, and all you have to do is apply them to that mathematical equation. Now, I want to point out that points of interest do not count. It's only just the joints and the pins that and the links that we're going to use. Okay, so it's that simple. Now let's apply it to this problem. This problem is on 12 and 13. I think if you turn to that page, then you'll be able to follow along. Actually, what this is I think that hold-on clamp that you might have drawn in drafting. I'm not sure. But if we set up the kinematic sketch, or kinematic diagram as we call it, and identify the links and the joints using numbers for links and letters for joints, then we can count up how many links and joints that we have. And in your given, list what they are. Now, we don't have any higher levels. There's no gear or no cam involved. So as the format has been stated earlier, box your formula, make your substitutions, show any kind of computation if you wish, and then display your answer. Now, because it's a mathematical formula, and the answer here was 1, then we convert that mathematical answer into what kind of mobility you have. And in this case here, we have a constrained mobility. So that is the whole point, is to discover how many joints and links there are and what kind of a mechanism movement you have. In this case here, we only need one operator. Basically, what we'll do is apply this to the sketches that you've already completed. Okay? Well, thank you very much.